Okay, so in this video we aim to find a way to compare vectors that is a more straightforward, more streamlined approach. Because if we had a bunch of vectors in a plane and we we're tasked to determine which ones are equal to each other, what's the magnitude of each of these. So it helps to just have a better approach to just graphing the vectors and to describing them, right? And the first step in doing that is to define something called standard position. All right, so when we talk about standard position, we're referring to the initial point being at the origin, right? So the origin here being 0, 0, and then the terminal point just being somewhere out there, x, y. All right, so any vector in standard position has the same property that its initial point is the origin 0, 0. Okay, so that leads us to being able to define what is the component form. All right, so the component form will define a vector v to be written like this, right? Where x and y are scalars, right? X and y are what are called the components, right? And in this particular, when it's written like this, right, these brackets, right, or not these brackets, these kind of symbols here, right, it is implied here that v has an initial point of 0, 0. So in other words, we're implying standard position when we write a vector in this form. We have v and the scalars x and y, its components, right? V has initial point of 0, 0 and a terminal point. Excuse me here. Of x, y. All right, so if we have some vector 1, 2, -1, -1, right? So both of these, right, common u, w, w, right? So for u, right, both of those have initial point at 0, 0, and then 1, 2 here. So that's the point 1, 2. Then the vector u is this vector here, and the vector w is this one here. That is the vector w. Okay, so when we write it in the component form, it is implied here that the initial point is 0, 0. In other words, that it is in standard position. Okay, so that's going to be very helpful to do calculations. Right. Now, if a vector is given to us that is not in component form, we are going to be able to change it to component form. Right, so let's say we define a vector between two points P and Q. Right, I'll call P to be xi, yi in terms of like initial, and Q to be xt, y sub t, right, terminal. All right, and then the vector v to be this vector here, v. All right, we can write this in component form, right? So in other words, it gets rewritten with an initial point of 0, 0, here, this vector v, and the way I find its components, right, and this is just called at some point just xy, right? The way I find these components of v is to take the difference between xt, the terminal point, minus the initial. In this place, order matters. Okay, so we'll always start with the terminal point, and then yt minus y initial. And that is how I change my vector in space into component form, right, in standard position. Okay. All right. Excuse me. So now we can find the magnitude, right? Now we can define an operation right? Some kind of calculation to find the magnitude, right? So if we think of here, when it's in standard position, the length here is y and the length here is x. And what we have is a right triangle, right? So using the some right triangle trigonometry, or not trigonometry, the Pythagorean theorem, right? We can define how to calculate the magnitude. And we'll denote it by these symbols here, like a double absolute value. Now, some textbooks, ours uses this double absolute value. Some textbooks will just use the absolute value itself, right? And if you really think about it, the absolute value along the number line is a magnitude operation, right? It tells you the units you are from the origin, right? Just the magnitude, right? Not direction, right? If it's a -2, that tells you what direction, but the magnitude of that, or the absolute value, that's 2, right? So some books just don't make a distinction between that. And again, it's just a matter of context, right? What are you taking the magnitude of, right? Is it a real number or is it a vector? If it's a vector, then we introduce this operation here, which comes from the Pythagorean theorem, or the distance formula, which is just, again, another form of the Pythagorean theorem, really, the distance formula. But that's it, right? That's how I find, now I have a calculation that I can do, right? Instead of comparing lengths, right? Now I can actually have a calculation that I do to find the magnitude of vectors. And now we can go back to our previous operations of scalar multiplication and addition. All right, so multiplication and addition. And I can redefine, or not redefine, I can just define them in terms of its components. Right, so if we let v equal to just some vector with components x1, y1, and w to be some components with x2, y2. All right, then and we'll let k be some real number. Then we can define our scalar multiplication in the following way. We could say k x1, y1. Then we can just rewrite this as kx1, ky1. Actually, we just multiply each component individually. All right. And in terms of our addition of two vectors, we have x1, y1 that represents our v. And then for our w, we have x2, y2. And this we can just write it as the sum of its components. All right, so we got x1 plus x2, and then y1 plus y2. So now we can redefine our scalar multiplication and addition with our components. All right, and now the last thing here in terms of vectors in the plane is this idea of a unit vector. So a unit vector is any vector that has a magnitude of 1. All right, so if you take the magnitude of some vector u and it is 1, then we define that to be a unit vector. Right, again, the magnitude is just the length of it, has nothing to do with the direction, right? So now if we have any other vector v and we would like to have it be a unit vector, and it can be convenient in terms to compare vectors, or to have vectors of a certain distance or length, I should say, in a given direction. Then if we have the starting point to be a unit vector, then it's just a matter of scalar multiplication. All right, so here in this case, let's assume v is not a unit vector. All right, so it's not of length 1, some other length. I can easily change, or I can easily find a unit vector that is in the direction of v. All right, so here, let me write that down here. It's a unit vector in the direction of v. All right, so here, so I can transform a unit vector in the direction of v by performing the following operation here. Take 1 over the magnitude of v. And so this is a scalar, right? So again, make sure we understand the context of what we're dividing. We haven't defined vector division, right? In fact, that is not defined, but this is not a vector, right? The magnitude of v is a scalar, it's a number. And we multiply that by v. All right, so performing this operation returns a unit vector that is in the direction of v. So let's do an example here. Okay, so let's say that v is equal to 1, 2, and I want to find a unit vector. A unit vector in the direction of v. All right. Excuse me. So the first step here is to find the magnitude of v. All right, so finding the magnitude, we get, take the components 1 and 2 and square them. So here we get 1 plus 4, so square root of 5. So that is the length of v, all right, the magnitude of v. Now a unit vector, excuse me, let's go back here. Let me made a bit of a error here. I didn't mean the magnitude of u, I just meant the unit vector u is equal to 1 over the magnitude of v times v. Okay, so now our unit vector is going to be 1 over root 5 times 1, 2. 1 over root 5. 2 over root 5. Okay, and then we can see by performing the magnitude operation on u, 1 over root 5 squared plus 2 over root 5 squared, we get 1/5 plus 4/5, which is 1. And again, there is our unit vector.